coming. My name is Mark Brown. I'm the applications engineer for the UK and Ireland, but I also support my friends and colleagues in Europe, South Africa, the Middle East and Australasia. So I've put this presentation together as I've seen lots of test engineers struggling with testing large test items on shakers at low frequencies. But this presentation hopefully will also help those with shakers with limited capabilities to make the right choices in their testing in the future. So let's get on with the presentation. For those that don't know vibration research and its products, vibration research designs and manufactures vibration control and data acquisition systems, supporting vibration testing on electrodynamic and servo hydraulic shakers. The 9500 and the 10500 are our best-selling vibration control hardware. They're capable of between 128 channels and 512 channels. Its features include sampling rates up to 256 kilohertz with either 4 outputs on a multi-shaker system on the VR10500. VR controllers have high-speed RISC processors that can process large data sets and efficiently run vibration testing at low and high sample rates. So we also offer a data acquisition system called the Observer 1000, and we also offer a range of small low-force shaker systems to allow people to the convenience of buying a turnkey solution. Vibration research core focus is to make the world's most innovative sound and vibration technology tools, enabling our customers to make reliable decisions and trustworthy products. Our core values are collaborate, capable and competent, accountable and responsible, strong and driven work ethic, and do the right thing, and innovation. And hopefully you'll see in this presentation that we're looking to ensure that you do the right thing with your testing. Here's the history of innovation for vibration research. So right back in 1995, the field data replication package was released and really made it stand out in the market from other controllers back in 1995. This module allows you to one-to-one replicate field environments in a non-iterative process. Underlying algorithms allow your field data replication test to reach full level quickly and save time. In 2005, we brought out Gaussian control, helping our customers more understand their random environment and allow them to add high peaks back into their random tests. In 2010, we have our field fatigue damage spectrum, where you can accelerate tests from field data very efficiently. Instant degrees of freedom helps you run the short duration test or bring yourself up to your full test level very quickly and allow you to see any control errors at the start of a test. In 2020, you've got our STAG analysis software for the generation of Sine random tests. And then more recently, in 2023, you have our TrueClip package, and we'll discuss that a little bit later on, where we can now closed loop control on acceleration, velocity, or displacement. Okay, so today's mission, I've run out of displacement on my shakers. There's 4 questions I've put myself on this so how much displacement do you need to run your test? So we'll take a look at that. How much displacement does my shaker have, and issues associated with displacement use on shaker systems, and what are my options if I don't have enough displacement available to me. And at the end, we'll take a look into vibration view in both Sine, random, field data replication, and shock, and have a look to see how vibration view can help you. Okay, so determine the maximum displacement of your test specifications. So I've set myself a scenario where we have an electrodynamic shaker system with only 25 millimeters peak-to-peak displacement. Our tests that are going to set ourselves, we've got a Sine test of 2G peak running up to 200 hertz, but what should our lowest frequency be? So we'll have a look at running some Sine sweep and some resonance searches and having a look at the response of our structure. We'll also have a look at a random test, a tar patch test, displacements above 25 millimeters peak to peak, and just having a look at how we should run this test and what options we have available to us. I have some field data replication, so I've got some racing car data file with an unknown displacement, so we'll have a look at running that test. And then finally, we've got our shock test of 40G, 11 milliseconds half sine, and we'll have a look to see whether we should run this test on our shaker system. The test item that I've set ourselves is it's a large flexible structure with several resonances believed to be less than 30 Hertz. So we should confirm this though. Okay, vibration view can help us calculate the displacement required for each of these tests. Okay, so the test that we're running from our Sine specification, so the lowest frequency that we need to run. So we'll investigate this. So before we try and run our test at 2G peak, we should look at an exploratory test to find the lowest natural frequency of our test item in its test configuration. Probably at a low test level, but we should also check for response linearity when running our full level test to make sure that our response has not drastically changed. So we should do this and take care not to break the test item, and also ensure that when we measure any resonances on the test item, that we're not measuring the response of the shaker test out of itself. Are we actually measuring the bending modes of the test item, and that we're not just looking at the shaker suspension and guidance system modes? So this is where you're rocking on your bearings or your suspension systems, and I've seen this quite a lot recently when people are doing Sine resonant track dwell testing, where they've done their Sine sweeps, and they've actually picked up the motion of the shaker and not actually looked at the bending of the product. So please check your transfer functions and look for the phase shifts, and really try and understand what your product's doing on your shaker system. So ensure that you're not just picking up a resonance of your test setup rather than a resonance of your product. Quite often you'll see this where the SRTD test, you're running at the resonance of the shaker system, and quite often you'll end up breaking the shaker quite quickly because you're dwelling at the resonance of the shaker system. Okay, we'll have a look at our random specification. So this is an extract from it on the left there. So we'll have a look at what displacement does the test need. We'll have a look at should we be using clipping, which clipping method we should be using. Can we reduce the frequency range or the low frequency amplitude of our test? Are there any rules around limiting the lowest frequency of a test? So we'll have a look at our field data. What displacement does our test need? What can we do if the raw data is higher than our shaker's capability? So what are your options in relation to filtering? And then finally, we'll have a look at the shock specification. So we've got our 40G 11 millisecond shock. We'll have a look at the compensation pulse options we have. So shocks on shakers require compensation pulses to ensure that you're at zero displacement and zero velocity after the shock has been performed. And we'll have a look to see whether we can perform this test on a 25mm displacement shaker. But then we'll also run whether we should run it on this shaker with high compensation pulses to achieve the 25mm displacement. Okay, so before we move on, I just thought I'd have a look at shaker limitations with regard to low frequency testing. So the kind of issues associated with low frequency testing on shakers. So the main types of shaker systems that we look at are just single axis shaker systems, electrodynamic shaker systems. So historically, ED shakers really only ran up to 25mm displacement if you've got an older model, but you now have shaker systems pushing 3 inches, and some of them are going to 4 inches or 100mm displacement nowadays. So there is the possibility to improve your shakers and go all the way up to 3 or 4 inches displacement, so 100mm displacement. But a lot of you people out there will still have older shaker systems that are running at 25 or 50mm displacement. So there are servo hydraulic shakers out there. Generally, these will have much larger displacements. Just in the last week, I've been working with an earthquake test facility that had over 300mm displacement. And before that, I was at a university that was doing human rated vibration with a meter stroke hydraulic shaker system. So there are really big hydraulic shaker systems out there with very large displacements if needed. We'll also take a look at vibration isolation systems. So how do we stop all of this low frequency force acting on the floor of your building. I've been at systems not too long ago whereby you could see the whole floor of the shaker building actually started to move, and you're getting resonances building up within the building and settling of the floor under the building. So really must understand what's required and what are our options in relation to isolating these low frequency forces in the building. So we'll have a look at the vertical situation, and we'll also have a look at slip tables and looking at airbag isolations and reaction masses. And we'll have a look at the issues with isolation systems and testing at low frequencies. So just having a quick look before we start, just having a look at what I mean by the shaker guidance system motion. So we need to ensure that when we're doing our measurements on our shaker systems, that any offsetted mass or any kind of unbalance within the shaker system could be causing our suspension systems or the whole shaker body and the isolation system to be rocking side to side and wallowing around. So we're looking at these kind of rotational aspects. So we're not looking at bending modes or our test item or our fixture or our head expander. This is where we're getting low frequency movements of our either our support structure within our shaker system or the shaker body, and the isolation is causing the whole system to move around. And this can be a lot lower frequencies than you think. You might have bending modes associated with your head expanders, but these motions can catch people out and be a lot lower frequencies than they think. So this is the other issue that you may have with very large test items. Some of the big electric vehicle battery systems are absolutely huge nowadays, and you're going to get these low frequency bending modes coming in of your head expanders and fixtures. So this quite often causes quite high amplitude cross-axis motions. So be careful on those as well, or with very, very large fixtures. But generally, what's catching people out is the suspension modes being the problem. So we'll have a look at shaker displacement capabilities. So these are a range of shakers from different manufacturers, and you'll see there's very different types of isolations of the body. So there's linear air suspensions, hard mounted trunnion systems that will probably need to have large reaction masses underneath them. And there's a 3D shaker system there as well. So just quickly looking at sort of some of the principal operations. So the other thing to bear in mind are certainly on ED shaker systems or even hydraulic systems with high displacements is having a look at the flexure system and the supporting system for your guided system. So we can get quite a lot of distortion going on at these high displacements because of the kind of returning forces on any flexure systems. So really kind of you need to look at your time waveforms when you're looking at high displacement tests to see how much distortion you're getting there. So air-cooled shakers, quite often you've got an airbag underneath the main shaft to kind of give you that internal load support. So any mass that's put on the shaker system, you're pushing up against it. So you've got that kind of restoring force there. Water-cooled shaker systems, most of these I think have got pressurized bodies. So they, the whole body of the shaker is pressurized in order to keep the armature up in the air with high loads on it. So yeah, please, when you're doing large displacement tests at low frequencies, please look at the waveform when doing any sine tests to ensure that you've got something that at least resembles a sine wave when you're doing these tests. So you might pick up any kind of non-linearities at the end of stroke, any linkage problems there, or you might pick up noise as the system runs up and down its bearings, which you might see. So depending on your isolation system, you're going to see some kind of distortion at low frequencies. So with vibration view, take advantage of our analyzer functions and maths functions in vibration view and check that total harmonic distortion and or the signal tolerance, calculate the signal tolerance and check those and making sure you're within the requirements of the standard you're working to, whether that's 600, 68 or one of the other standards such as MIL standard 810 or the DEF standard. Also, make sure you're checking the cross-axis accelerations just to make sure that you are getting linear motion and you're not getting any rocking from side to side. So ensure that you're not seeing those. So with our total harmonic distortion within vibration view, we're looking at the first 10 harmonics and seeing how much their amplitude is compared to the main signal. Also, signal tolerance is where we're comparing the filtered and unfiltered RS values of the waveforms. So looking at shaker isolation systems, so the basic system on the left there, the pneumatic base isolation. This is the sort of simplest and most least expensive that you'll find on sort of cheaper or the low end shaker systems on the market, the low force ones generally. They can cause problems with low frequencies. There'll be a lot of wallowing around at low frequencies. So quite often these shakers will be spec'd to not have a low frequency capability, but you will probably be able to drive them at low frequencies. So it can be tempting, or you may unknowingly run it way below its requirement. And generally these systems with base isolation don't fare too well with long compensation pulses on shock tests. So that's the kind of, you'll see that. So this is base isolated pneumatic systems. The middle there, you've got a hard trunnion system. So you've got a kind of turning point here, a trunnion mounted that's hard mounted. So these will transmit vibration forces to the surrounding building foundation. So generally, if they're of any substantial size, you'll need some kind of seismic mass underneath them, or an isolated seismic mass. So you'll need to have isolation underneath that seismic mass. So the seismic mass is there to basically add mass to reduce the movement, and they act as a reaction mass for you. The one on the right there, you don't really see these very often, but you'll see them on really small shaker systems where you've got little isolated feet, but you've got it as a trunnion system, so you can rotate the shaker as well. Obviously, these again don't correct any of the wallowing that you'll get on a base isolated system. So the most popular for higher force rated systems and more expensive system is the linear air suspension system, whereby you've got airbags and shafts that restrict the isolation and keep it as the body moves up and down isolation in a linear direction. So this is far better for doing tests at low frequency, and you can try and maintain a linear motion with these isolation systems. The trouble is with them, you're just reacting the body mass of the shaker system. So depending on how much mass you put as a test item on top, you'll get body movement. And I'll show you the quick calculations on linear air suspension and isolation systems. So you'll end up losing some of your shaker's capability with the body movement up and down, depending on the force level that you're using and the size and mass of the test item. The other one, simpler one there, is a combo or mono base on the right when we're doing horizontal testing. So you've got a combo base where the shaker rotates sideways and pushes horizontally to a slip table. The base isolation on this is often either rubber pads, machine tool pads, or an air isolation system. And depending on the manufacturers, you'll get different amounts of compliance and the flexibility of these pneumatic mounts. So as you can see from the arrows there, you will start getting rocking backwards and forwards and pitching and movement on these systems if you're buying a combo mono-base system that just sits on your laboratory floor. So here's some pictures of real shaker systems in the combo there. On the left, you've got quite a flexible system there. The one in the middle there, these normally, or the sort of slightly to the right there, these normally have rubber pads underneath them and are not as flexible, but will transmit more energy to the surrounding floor and the structure of the building. So if you really want to run for low frequencies, these combo bases, generally you're not wanting to run them much below 5 Hertz, depending on the size of them. It does depend, but it will be in your shaker's manual. But really, you're not going to be wanting to run these with any kind of high masses on them because of the amount of pitching and rolling you're going to get on them. If you're trying to run to lower and lower tests with higher and higher test masses, then you'll start to look at systems like this where you'll be running with a bigger mass underneath your shaker, and your air isolation systems will be more involved underneath the floor. Generally, people put these systems into a pit to kind of reduce the working height of the shaker system, but this adds substantial amount of reaction mass to your shaker system, certainly for the horizontal and the vertical operation as well. And then the ultimate system will be a huge seismic mass below ground on air isolation systems, where you're trying to bring the center of gravity down as low as possible. So any pitching moment is kind of in line with the airbag suspension system. So you're trying to stop that mass above the isolation system. So you're trying to bring the center of gravity as low as possible. So with all of these isolation systems, you're going to get a region of amplification and then the isolation period afterwards. So generally with most linear air sort of suspension systems, you're talking sort of between 3 and 5 hertz on most of those. So most of the shaker systems, you'll be looking down at those kind of values. Here's some very big facilities I thought to show where these ones, where the whole working area, the head expander is all below ground, and the whole area is kind of the seismic mass. So you've got multiple shakers on a big shaker cluster there. And this is another one with the bed plate with the isolation underneath. So this is for testing large items with remote bearings outside the sides of the shaker system, the slip table. So just looking at maximum displacements and looking at armature deflections here. So shaker body, there's an equal and opposite reaction opposing the large, pushing the large masses reduces the available displacement. So shaker body masses versus payload mass is the important reaction feature here. So we'll have a look at the equations associated with that in a moment. So what we're looking at here is, depending on the mass of your armature and payload, divided by the mass of the armature and payload and the shaker body, times that by the displacement on the armature, gives you that kind of reduction in available displacement. So you can see here that the more payload you put on there, the bigger this amount of body movement that you're going to get on the shaker system, just by the fact that you're pushing a higher mass above you. Obviously, the bigger the reaction mass, the body or the seismic body below you will reduce that displacement limitation that you're getting from testing the higher mass item. Okay. So just a word of warning with the isolation systems at low frequencies. If you do run your shaker systems into these low frequency isolation areas, you will get kind of amplification, and you'll see that depending on the amount of damping that is involved with your isolation systems. Okay, so we've had a look at shaker isolation and the problems at this, but do I need to test to such low frequencies? So what are our options if you can't afford a brand new shaker system and you need extra displacement? So we'll have a look at what do some of the test standards say. So we'll look at MIL standard 810H and the DEF standard W35, just to see what they say about this. And also there is another point to take into account, is why do some profiles stop at different frequencies? So when you have a look at the lowest frequencies in tests, if you look at like the aerospace standards and the MIL standard, so they are assuming the fact that you're testing test items that don't have resonant frequencies below these frequencies. So if you look at the MIL standard, it says that they're not expecting you to put test items into planes with resonant frequencies below 10 hertz or 20 hertz. So they're assuming the fact that you're testing items that don't have such low natural frequencies in them, and the fact that if you are testing items down with those, that you will extend the frequency range to lower frequencies. So that's kind of one reason why you're seeing there, is that they're making the assumption that you don't need to test to such low frequencies. But there'll be lots of people out there that have small test items that have frequencies, natural frequencies much higher than these lower frequencies. And you can look at cutting the low frequencies from your test profiles. So we need to ensure that we are measuring our natural frequency or our test items if we are to go down this route of restricting the lowest frequencies within our test profiles. So we need to make sure that we're not looking at the kind of rigid body modes of the suspension system or the isolation system of the shaker. So taking a look inside these standards, so if you look at the lower frequency, so the general rule of thumb is tests should be conducted at frequencies lower than half the lowest flexible mode of frequency of the test item. So if you look at Annex A 2.3, the random vibration frequency range, typically the low frequency is 1/2 of the frequency of the lowest resonance of the material or the lowest frequency at which significant vibration exists in the environment. Okay, so this is what we're looking at in the test standards. So within MIL stand 810H, again, 2.7.3. So if you look at test 514, the low frequency limit, the exposure frequency range encompasses the application frequency range. Use a low frequency limit on the range that is the low frequency limit of the application environment, or half of the lowest material resonant frequency, whichever is higher. Okay, so this is the kind of associate. So if you are going to do this, you must really talk to your test specifier and your customer and make them aware of what you're doing. I know this isn't going to always be easy, and the people that give you your test specifications aren't necessarily experts themselves. So this is more advice from MIL Standard 810H extract from Annex C. So again, we should be looking at doing modal surveys of the fixture and the test items and looking at all of those resonant frequencies. Okay, so we'll carry on and we'll have a look at how Vibration View can help. Okay, so looking at our Sine testing, so we can check the specification percentage against our shaker displacement limits. So with Vibration View, you can specify on a Sine test your starting amplitude in millimeters peak to peak, and you can work out what the crossover frequency is automatically with your G level. So, and then at the bottom of the screen there, you can see that you can check to see where your displacement limit is in relation to your shaker. So if you hang over these limits, it'll tell you how close you are, and you've got the bar there at the bottom of the there. Obviously, what the idea is, you carry out pre-test resonance sweeps, look at the transmissibility in the phase plots to understand that you are identifying the test item resonance and not a shaker or fixture resonance. Remember that when an item goes through resonance, the phase will transition through 90 degrees and end up 180 degrees out of phase compared to the input. The key is to compare the correct reference positions. So you need to make sure you're looking at the right reference positions, so that kind of input to the test item and looking at where the bending is happening. So it's really important that you kind of make sure that you can visually understand your amplitude and phase relationships and see what's bending. The advice from the test specified customer is that no resonance is within 2 or 3 times the lowest frequency. So yeah, I mean, to give you more comfortable, 2 or 3 times is sometimes specified there, and check that you can do it within the displacement capabilities of your shaker. So on random vibration, obviously you can paste your breakpoint table profile straight into Vibration View. It's very easy to do. You can check your displacement against the shaker limits. You can adjust your PSD lines to ensure that you have at least a quarter resolution compared to your lowest frequency breakpoint. So that's an idea. Sometimes you can do it to a half, but my advice would be to go to a kind of quarter of your lowest frequency breakpoint on your PSD schedule. And again, use half of the first natural frequency as the guidance for your random test. And then what Vibration View has, it has some clever clipping available to you. Try our new innovation TrueClip. TrueClip displacement will try and keep your displacements, or will control your displacements to a sigma value of your choice, and ensure that you don't get any displacement trips going on your shaker system. So just to see whether you all understand what clipping is, so Vibration View has different drive clipping methods, but until recently we've all been looking at open loop drive clipping of the drive voltage going to our amplifiers. This doesn't give you acceleration clipping as you might expect it to. With the shaker and the amplifier in the way, you will still see peaks higher than 3 sigma or 4 sigma, whichever clipping value you choose on it. And also, depending on your drive clipping method, you will also be distorting your waveform and creating frequencies that you didn't intend to create from your test profile. So VR has come up with the true clip. So if you haven't seen it yet, get your local VR application engineer to demonstrate true clip to you on your shaker systems. It's a clipping method where you can ensure that your displacement peaks are kept within your defined sigma value. So we can have a look at that. So I'm hoping that people are aware of what the probability density function is. You can see on the right hand side there, and you can see the effect of clipping on your drive signal. So just to give people an idea of clipping, I just thought I'd put this up just to kind of give you an idea of it. So most people have heard of 3 sigma clipping, but do you know how much clipping is going on when you're doing 3 sigma clipping? So to give you an analogies here from a spelling point of view, whatever, with 3 sigma clipping, you're kind of having 1.5 misspelt words on a page in a book. With 4 sigma, you'd be looking at 1 misspelt word in 30 pages in a book. So that's a kind of quite a substantial difference there in relation to the amount of clipping that would be going on. If you have a kind of look in times with 3 sigma, you'd be looking the equivalent of 3.5 months in a century, where 4 sigma, you'll be looking at 2.5 days in a century. So you can kind of see the difference between those 2 values of 3 and 4 sigma. So, I mean, our advice is only use clipping if you have to. From that's the general advice in the standards, is only use clipping if you have to, and obviously displacement limitations is one of the reasons why you might use clipping. So, but yeah, you should only use clipping if you have to, and then if you are using clipping, you must, or you certainly should always be reporting the fact that you are using clipping. I know there's a lot of people out there that their default will be 3 sigma clipping and they don't report it to customers, but their standard tests have 3 sigma in them. So just be aware of that. Okay, so I'm going to fire up vibration view in a moment, and we'll have a look at doing some sine sweep and how we check for resonant frequencies, looking in the software to do that. We'll look at this tar patch random vibration and have a look at the clipping, and also we'll have a look at frequency resolution on the effects of displacement. We'll have a look at field data replication filtering, and we'll have a look at shock compensation pulses. Okay, so what I've got here, I've got a sine displacement test here that I've set up. So what it is, I've got a shaker system that's got 25 millimeters displacement. I'm just going to run out a 1G test here as a pre-test, and we're just going to kind of check. So if I put in the 24 millimeters peak to peak, just putting a notional start frequency of 3 Hertz, that's the lowest frequency I'm allowed to run the shaker with, and we'll just calculate the end frequencies calculated there at 4.5 Hertz. So we've got our constant displacement here up to 1G until we hit 4.5 Hertz, and then we're running at 1G after that. So that's the easy way of putting in a sine test. So we'll run this test again, and you'll see it build up and quickly sweep up from 3 Hertz. Here we go. And what I've got, this is set up, I've got some resonances built into the channels here at fairly low frequencies that will be running as we do there, and I've got our auto annotation set up here, so we'll pick the peaks up on our tests. I've got a transmissibility graph running here along with a phase relationship below it. So as we see, we'll sweep up and we'll accelerate the frequency in a moment, and we'll see the results come through in a moment. So with our test running here, just having a look at the parameters that we've set up here. So we've got our input filters set at 5 Hertz and a 50 Hertz, 50% fractional bandwidth here. So this is where what we're seeing back on the screen here is just the drive frequency with a a band either side of it picking up there. So we can see our first frequency is appearing up here at the moment. So it looks like we are going to be around about 9.5 hertz there. And our next frequency is 15 hertz there. So what I've got set up here, just for those that don't know, we've got our auto annotate settings on the graph. So the way we're selecting our peaks is we're trying to select the 4 highest peaks with a transmissibility selection method above 2, and we're going to sort them from low to high frequency with our minimum spacing to ensure if we had noise on the signal that we don't get 2 peaks too close together. So we're going to use these auto annotate settings in determining the frequencies we get here on the graph. Okay, we're almost through to the end of the sweep. So if we look at the transmissibility plot, you can see that we've got our phase shifts are occurring at each of these resonant peaks that we've got on the different channels. Okay, and here we've got our peak displayed, our peak values displayed. So there we've got our resonant frequency. So because our first natural frequency is at 9.5 hertz, we could run this test or request that we run this test only from sort of 4.5 hertz. So that's at that point there. So we could get rid of this. So within our shaker system, we could run this test at this level quite comfortably with a lowest natural frequency of 9.5 hertz there. Okay, so that's our resonant frequency done. We know what our lowest frequency of our test item is. So we'll just have a quick look at our random test. So what we'll do is, so what I'm going to do is just show you the feature of cutting and pasting our random profile in. Get our Excel to open up as well. Okay, so this is our tar patch information. So we're running quite a low frequency test. So if I drag this over, just copy that. And if I paste this in here from our clipboard, so we'll see now that we've got a test whereby it's a 75mm displacement test here. So we can't really run this test on the shaker system as it is at the moment. So what we would do, we would just select that 4.5 hertz and go, this is going to be my first data point. And there we go. Oh, look, miraculously, I'm within my my 1-inch displacement on this test. So that's what we could do in this instance, is just run this test from 4.5 hertz. As long as we've told our customer that's what we're going to do because of our lowest natural frequency of our test item. So the other thing I was just going to quickly show you was have a look at the effect of our frequency resolution on our displayed displacement. So if I was to drop down to 1 hertz displacement, the 1 hertz frequency resolution, just to quickly apply that and then have a look at our peak to peak has gone up here. And that's basically because that first block that we've got there is now plus or minus 0.5 hertz either side of that. So we're actually putting energy out all the way from 4 hertz. So we're just grabbing a little bit of extra displacement because of that first resolution block there is 1 hertz wide. So it's actually showing us data from sort of from 4 hertz to 5 hertz in that resolution block, and we're actually too high. Our kind of breakpoints are too close to have that as our resolution anyway. So if I go back to our parameters tab and put it all the way back up to a 1/4 hertz resolution now and apply that, we'll see now that that peak to peak is now changed. So it just kind of shows you the fact that you need to know what your frequency resolution is to get a true picture of your peak to peak displacement. Okay, I'm sure you've all seen random test run, but those that haven't will start this test up. And what I've got on here is I've got our IDOF functions running, so we'll come straight up to level. And for those that are not used to it, we'll bring it straight into full level, and then we'll have IDOF will kick in after 4 frames of data. So once we're running, and it'll clean it up and get rid of our control errors, and we'll see that our true mean of the signal is smack bang on the demand line. So you can easily see by going straight up to full level that we're in. So we're not relying on any of our pre-test levels or our level scheduled levels and data from that and multiplying up. This is all just from 4 frames of data at the full level. So it's a really good feature for those doing short duration tests. You can immediately see that you're within tolerance and you've got no control levels there. So I'll just have another look. So I'll just have a look at the waveform here. So I'll just double check to see what I've got as my settings when it comes to my clipping parameters. So at the moment, I've got silent clipping on and 3 sigma clipping. But if I was to turn it off to no clipping, stop this test and restart it. Okay, I thought they'd restart. So we're now getting peaks in the test that will become higher than our 3 sigma value. So these lines I've put in here are the 3 sigma value. So now you can see that we're getting quite high peaks in the signal here with no clipping on at all. So if I come along and put on our true clip, so I'll just do acceleration true clip rather than the displacement clipping to 3. So if I apply this now, I have to stop the test to change the clipping to true clip. Okay, if I run this test now, we should see that we'll just hit the acceleration limits at 3 sigma. Okay, here's the waveform building up. Okay, you can see now that we haven't got those big extremities and we're keeping it to the 3 sigma limits now. So our peak to RMS value is now kept within 3 sigma limits. So this is a closed loop control system now that's ensuring that these peaks are kept to within the 3 sigma limits. So just for those that haven't seen the probability density graph that we have the function of showing, so what I've done is I've got Gaussian, there is that nice curved line. I've got the no clipping equivalent on there, so you can see all of the peaks with no clipping. I've got our silent clipping, so if you can see where I'm highlighting the 3 sigma silent clipping there, and then I've got the displacement clipping. So the displacement clipping is kind of changing the shape of the Gaussian a little bit. So it's still allowing acceleration peaks to occur, but it's keeping our displacement within the correct, and it's doing that by manipulating the shape of the Gaussian slightly there. Okay, and then, so the other one I just thought I'd quickly show you is you can get your resonant frequencies from your random test. So, but if you are using our cursor with auto annotate on the PSD graph, it's actually picking not the peaks of the PSD, but it's actually picking the peak transmissibility. So you can see here it's not picking the peaks up of the PSDs, it's actually picking up where the peak transfer function is. Okay, so it's taking these peaks, not the peaks from our power spectral density. So just be aware of that. If you're using our auto annotation functions, it is picking the peak transmissibility. Okay, so I'll stop that test. Have a quick look. I've got some fill data here, so I'll quickly play this test. So if we edit this test, if I just show you the edit function, so we brought this waveform in, and we can have a look. And if I just change the filter settings to 3 and apply here, so if I go back to the kind of capabilities of the shaker. So I've set that the filtering are minimum filter range from 3 Hertz to 4 kilohertz. And now I can see that I've got a displacement on this test of 67 millimeters peak to peak. So obviously we couldn't run this as it stands on the shaker system. Look at our filtering options. So if I now say that we want to filter it at 6 Hertz and look at the playback, that then brings us right within our 25 millimeters capability there. So that's a field data replication test. So if I quickly run that, just so you can hear a lovely Formula 1 car going around the track. So here's it building up to the right levels. So we can see that with our testing and our filtering that we've applied. Okay, so that's what we would do for a field data replication test. Okay, I'm just going to quickly load up the final test in our sequence, which would be our shock tests. So if I just have a quick look at this shock test and open. Okay, and I've just got a second one that I'll just open as well. And open the next one. Okay, so what I've got here is I've got our 40G 11 millisecond shock. Okay, so if I'm just going to start this shock going in the background just to speed things up a bit. So what I've got here is I've got full square optimized for velocity and displacement compensation. So I've got it set right up at 19% of the peak. So we're using the full 20% tolerance lines within 1% of those. And you can see this test is within 22 millimeters peak to peak. So within the shaker's capability here with this test. So, but when I run this test, I'll just show you a few things just to make sure. So the other thing I'll just bring in here is just this feedback control. At the moment, I've set this to the full range of the shaker system rather than our auto settings. And I'll come back to that later. So here is the shock. So it's carried out these shocks. And what I've done is I just thought I'd show you the shock response spectrum of each of our channels. So if I look at channel 2's response, you can see at the top here on the top right hand side, looking at the actual control response compared to the demand line. So the idealized pulse of 40G 11 milliseconds without any compensation would be this line. But the control, because of the compensation pulse, the shock response spectrum would look like this associated with it. So you can see from about 14 Hertz, we're kind of idealizing this SRS. We're under testing below that frequency, and then we're kind of quite a lot over testing above that frequency with this one here. If I go to my next shock that I've got here, okay, this test that I'm running here, I'm running this with a smooth reduced frequency content distortion, and I'm going to run this with only 5% pre and post. So you can see here I can't run this test with this shaker system. Because it's 95. So I'm just going to have to quickly change my shaker system to run this test. Okay, so I've just changed my shaker system, and you can see that I can now run this test. So if I now run this, we'll just show you the shock response spectrum again. So you can see now that I'm not under testing is right down at 4 Hertz now, so I can successfully run this test at with an under test from 4 Hertz on the SRS, if you're looking at the guidance on the SRS here. So you would say that with this 5%, you could run this test on our natural frequency of our product at 9.5 Hertz. We could successfully run this test, but you can see that I'm needing to have 95 millimeters peak-to-peak displacement in order to run this. So I couldn't run it on my 25 mil shaker system with this level of compensation. But it would be more correct to be running this test than it would be with my other test. So if I get back to my full compensation test here and have a look at the comparison between, so what I've done here is I've copied over the low compensation pulse, comparing it to this high compensation. So this is the one where we had our 19% compensation on here. So you can see that the difference in outputs between them. So the bottom one here shows you the response of the channel 2, where it had the 9.5 Hertz natural frequency on channel 2 with the low compensation. So you can see the response is very vastly different compared to the channel 2 that we've got from the high compensation test. So it's fundamentally a much reduced test with this high compensation being applied compared to the low compensation pulse. So you get a very different test here. Then if we look at channel 3, which had a natural frequency of 15 Hertz, you can see that actually we've got a much lower test with the low compensation is a lower test than this test where we've got this response here. So where we've got the compensation pulses amplifying in the shock response spectrum, we can see we've got a much higher response in the SRS from this channel 3. And then if we go to channel 4, you can see that we're getting a lot different again there. So that's the difference. And you can see that in the time waveforms as well. So if we look on the time waveforms here, if we look at channel 2 on the low compensation pulse, we've got a peak G of 10 G here, where on the high compensation we've got a minus 7.5 G. So that the peak G is only 7.5 compared to 10 G on the low compensation. So you can see we're getting fundamentally a different shock depending on which compensation pulse we have here. So that's it. Okay, I'm just about done now with my presentation. So if anybody's still there, I've just about finished. If you've got any questions, then please get in contact with us at Vibration Research, and we'll see to answer them. If there are anybody that wants to put a question in now, I'm more than happy to stay online and to have a chat with anybody that's got any issues with high displacement or low frequency testing. Okay, thank you very much, everyone.